Hi, can you guys hear me okay? Yeah. Okay, good. Good afternoon. As Kelly mentioned, my name is Emma Chen. I'm the Seattle District Sustainability Team Lead, and today's webinar will be on the ever-crucial window-to-wall connections presented by Mike Sebold and Peter Poirier from the Building Envelope Solutions team. As most of you know, each division was assigned a specific area of technical expertise. So Northwestern Division is the RECX for high performance building envelopes and for air barriers. Jeanette Feast is our Sustainability and Energy Program Manager. Nick Alexander is our air barrier subject matter expert out of Omaha. And I lead the NWD RTCX team out of Seattle District. At the bottom here is the link to the SharePoint site for our specific RECX on building envelopes. You'll notice on the top bar the site will contain tools, training, and references. Our intention is that we will be developing a library of details and specifications showing good building envelope strategies for a variety of construction types. There are links to the resources at the left, links to documents at the right, and there's an area for discussion threads at the bottom of the SharePoint site. Our team across NWD has put together training classes and webinars, and Nick Alexander just headed up the team that wrote the ECB and Field Guide for Construction Quality Assurance of High Performance and Sustainable Building Envelopes. He also teaches the Prospect course on building air barriers and pressure testing. The Passive House team provided reviews for Passive House compliance, and Kansas City District is It looks like we lost connection for a few minutes there, but I was just about finishing up anyways and getting ready to turn this over to Peter and Mike for them to share our screen and present their webinar. So they can go ahead and do that at this time if they're on.
Good afternoon. We just need the share screen link. Emma or Kelly, is there a share screen link? Here. Hello, Kelly or Emma, is there a share screen link?
This is Emma. I'm here, but I believe it's Kelly that has to share your screen for you. I don't have that.
Okay. All right, there we go. You should be seeing the full screen if we could just get confirmation for this. Sharing full screen. Emma, can you just confirm that you're seeing the shared screen? Thank you. Good afternoon, everyone. This afternoon we'll be addressing the window-to-wall interface, achieving a watertight connection. I'm Mike Sebold with Tremco, and Peter Poirier, our technical director, will be finishing up the presentation. Our learning objectives today are to demonstrate how the window-to-wall interface impacts the economic, indoor air quality, energy, and structural consequences of the failure to ensure long-term success of buildings. We want to identify connectivity options, including the advantages and disadvantages of each. We would like to recognize the importance of addressing the connectivity issues at the design stage, which will allow the ensuring of proper sequencing of installation. And then we also want to understand how on-site performance of the selected materials can be verified through real-world testing to ensure a tight system for long-term performance. Our overview is to talk about the window-to-wall interface and why it matters, to discuss connectivity options within the industry, to discuss connection failures, examples, and various product tests, talk about construction sequence and installation challenges. We'll discuss case studies, modifying connection details to meet the stringent construction practices, and we'll use healthcare examples. First, by talking about Children's Hospital in Milwaukee, Regents Hospital in Minnesota, the new Parkland Hospital in Dallas, and closing out with our discussion of the replacement hospital at Camp Pendleton in Oceanside, California. Now we'll follow up with questions and answers. So we begin with why do buildings leak? Despite all we know about buildings, we know the importance of sealing gaps, buildings still leak. The reasons for this envelope failure is there's no single source of responsibility for quality control, spec enforcement, building envelope integrity, and it all comes down sometimes to that we accept the low bid and lowest technically acceptable solution, which translates to failures. When we talk about envelope failures, they traditionally are at the interface. The Building Enclosure Council, as well as affiliated forensic specialists, concur that the majority of building envelope leaks investigated occur at the envelope interfaces. So what are these interfaces? Well, the window-to-wall tie-in connection is a transition between air barrier to window or curtain wall systems or cladding systems. Why is this connection critical? A continuous and secure seal protects against air and moisture infiltration. And why is this infiltration important? This is a critical connection to assist you in achieving the air tightness standards that you've set, as well as achieve the facility life and design life cycle of the building, to achieve the energy and mandates, as well as the reduced maintenance costs, to meet the new aggressive industry standards that will become building code in the coming years, in particular ASHRAE 189.1 update that will go into effect in 2015, indoor air quality, as well as risk management. And when we take a look at air leakage, the Corps has been very progressive, and this is a study that was published by Alexander Zetoff and Dale Herron of Searle that talks about the importance of air leakage and the significant energy savings that are a result. And as you can see, this validates the NIST study and gives merit to the energy mandates that there is a direct correlation between the air leakage and achieving your energy mandates, in addition to providing a better indoor air quality. So when we take a look at current practices in real-world installations, a lot of these current practices fail under minimum performance requirements. Okay? These real-world issues arise and are preventable, but mostly they lack proper coordination, the sequencing of trades, a quality installation, and on-site testing and commissioning, most of which the Corps has been addressing. So the current connectivity options within the industry are traditionally sealants. We've seen an influx of impregnated compressed tapes from the European markets. Spray polyurethane foams are commonly used, peel and stick membranes, and we'll close on talking about engineered transition assemblies, which really the market's moving to develop performance seals in these connections. So as we talk about sealant connections, they address air, liquid, and water vapor at the connection. They're traditionally a sealant or a urethane. They can handle a variety of sizes, but once you start getting to large openings, the sealants don't work that well, in particular over 2 inches. You need to address and match the proper sealant movement with the proper movement in the sealant joints. The windows must be set before these connections, and sealants are weather dependent. As we talk about pre-compressed tapes, it's a European technology which is unique because they address both the air, water, as well as a thermal control layer, which is very important in meeting your energy goals. These materials are commonly installed when the window installation occurs, and the gaps sometimes can be limited, but depending on manufacturer, you need to take a look at the sizes. But one of the big benefits are there are no temperature restrictions for these types of installations. Spray polyurethane foam is becoming a standard in the industry and not necessarily a good one in all applications. They still require sealant beads to make the connection to assure you an air and watertight seal. Proper expansion is required of the material, so you need to take a look at the application for spray foam. The spray foams traditionally have limited to pore adhesion as well as movement capabilities, and you also have a shrinkage potential. So although they look like they're short-term solutions for stopping air and water, the long-term effect sometimes is far outweighed. Peel and stick membranes are also commonly used for this connection, and one of the challenges for peel and stick connections, as you can see here, is corners and how you lap and treat the corners of window frames and actively moving joints. So in addition to the different materials out there, we need to take a look at compatibility concerns with respect to these window-to-wall conditions. In particular, when you have air barriers that traditionally use mastics for the connections, asphaltic mastics, that are coming in contact with sealants, whether silicone or urethane, you need to look at the compatibility. These traditionally can lead to leak point sources when the materials are not compatible. The other challenge in sealing these are the limitations with traditional methods is these large gaps of sizes in these windows. We're seeing larger and larger gaps in these openings, and traditional sealant and foam conditions can't transition these assemblies because the continuity, especially around hollow mullions or open-ended stems, becomes critical. And long-term performance of these materials are also critical. So this leads us to discuss engineered transition assemblies, or ETA. And what this is a combination of engineered materials integrated within the glazing and the air barrier systems to address air and water. There's no restrictions on the gap size, so we can handle small joints as well as large joints, as well as it passes the seismic testing, which a lot of the current solutions on the market do not do. This also allows for window installation before or after, which gives the contractor flexibility for sequence of installation. So as we talk about air barrier connections along with engineered transition assemblies, this will provide compatibility and a long-term continuity for your building envelope. These are some of the lessons we learned from U.S. Army Corps projects. Sometimes there's not enough details from the architects on the drawings to make proper connections. If a building fails the airtightness test, post-construction fixes, which are traditionally spray foam, traditionally become insufficient. especially as the building weathers on. And the critical connection between both the roof to wall and the window to wall has always been a connection that's been referred to as by others. There's a lack of responsibility in the trades within the field to take responsibility for this, which leaves some of the details to the contractor, which leads them to cowboying or creating field fixes for these solutions and not engineered solutions. So who's responsible for ensuring a tight seal at the window of the wall? I'm going to turn the presentation over to Peter Poirier to discuss that.
Good afternoon. Hopefully you can hear me all right. Typically, as Mike was mentioning, the architect is working with simple details taken from different wall manufacturers as shown. Typical pressure bar system. In this application, the contractor has indicated the perimeter sealant bead on the pressure plate is their primary seal. Another wall manufacturer will dictate maybe the seal needs to be on their mullions on the structural condition. But in either case, those are their primary seal for responsibility, but they're showing very simple sealant beads. From that, we went ahead and built the test jig. So we took a customer's pressure bar system and mounted it in a jig. And this jig allowed it to move for thermal movement, seismically, and we can also control the joints around the perimeter so we could increase it from 1/4 to 1/2 to 1 inch, whichever was the material we were trying to achieve or test. Typical application, as you're seeing on the screen, a simple 1 inch joint, the head of the window. As the sealant moves, the mullion moves down. Obviously, the sealant accommodates that movement. So this is the primary application. Works fine if it's properly installed. However, when you start looking at a vertical condition that we have here to the head condition, what you've got is a cut piece of metal. So we're just applying sealant along that cut edge. But as the joint starts to move, if you look at that location, if we had an incompatibility with the sealant that may have been used to seal the metal joinery, or when the contractor was cleaning it, may have left some debris along that edge, you may end up having a pinhole or a leakage point. And as this joint moves back and forth, that pinhole size will actually propagate and tear further through. So as you test it, but looking at it, you could never tell that actual hole was there until the actual wall starts to move seismically or thermally. Here we have an application where typically you see the wall being moved out for added insulation. Difficult connection to be made with a sealant bead when you have open ends of metal. So as Mike mentioned earlier, people started using peel and stick products to span unsupported gaps, which isn't designed to do that. Here we're wrapping a window in a precast condition, but as you can see up close, now the sealant is pulling away the peel and stick from the substrate, and potential leakage, and obviously aesthetically not pleasing. It'll bleed into the sealant, and we have a loss of bond. Trying to mix different materials for the air barrier membranes isn't very effective. This is a building where they actually had to start tearing off the brick veneer because the peel and stick products working with their weather barrier materials weren't compatible with one another. Obviously, the contact area were not very good, and so they had to replace everything. So to test those products, obviously we put it in the same jig. Here you can see the product does allow it to take the movement in the head, but as soon as it starts to extend past its installation, it will pull itself off. Looking at the jam condition, many manufacturers will indicate that they can span a 1/2 inch without an issue. But here we're looking at only 3/8 of an inch of movement, and what you're having is the product peeling off from the different substrate of the curtain wall. In this case, now you would think now I'm only spanning 1/4 of an inch of contact, it would be less of a problem. But here, actually the movement with still 3/8 of an inch creates more shear on the membrane and pulls itself off. This is just after one cycle in the opening. As Mike was mentioning also, people are using spray foams. In this case, metal panels had to be removed, spray foam was not effectively applied, and of course during any movement it compressed and left openings. So again, we applied the foam tape in the same jig to see what would happen. So the foam can get compressed, but as soon as it opens up nominally, just 1/8 of an inch, we lose that bond. It's never going to reattach itself, so we don't have a seal. The project solutions where we get into, as mentioned, one of the jobs was Children's Hospital. Written out the Journal of Building and Closure Design. This study was done completed in 2005. So taking materials that are used, This was a unitized curtain wall hung on the side of the building, and they had to make a connection between the air barrier and the wall system. Very difficult application for a sealant bead to be done. So we extrude silicone sheet and translucent, as you can see, being unrolled. They were able to actually adhere from this air barrier to the window system, so they could actually tie that together. But this was basically a Band-Aid effect. Wasn't designed to do it. They were actually able to do this for this condition, but trying to do it on the job site rather than design into it was not practical. So what we started to do is testing these components to make sure they're compatible with one another. So taking the sheet and testing it on aluminum, concrete, and wood and different substrates to make sure we can have a long-lasting bond. We also tested to ASTM C1518. This is a standard specification for pre-cured silicone joints. So this is a test method or specification for movement class and tear class. It doesn't dictate how much movement, but in our case, we were going to go ahead and test to 200% elongation versus 100%. So you would open up the length 200%, hold it for an hour, and then record any loss of adhesion along the way, whether adhesive loss or cohesive loss. We didn't do ultimate elongation because in this test method, they wanted to know cut tear propagation. So we ended up having to cut each system. But here is a plot. So you hold the membrane, hold it for 60 minutes, and then cycle it 10 times to make sure you still had a bond. After you cycle that sample, you take and make a 5mm cut, and that would tell us, did it zipper horizontally? So it would be a class T. In this case, the cut was made vertically. It zippered upwards, but this would be considered a class PT if the zipper had gone forward. At this point, this was just a classification. It does tear. Silicones do have low tear values. But we were more interested in determining if a puncture did occur, could it be repaired and still perform? So we took these samples after testing it for 200% elongation, put the cut, applied silicone, took, in essence, a tire patch, the same material, embedded it, and waited 7 days, and we were able to take 200% elongation. And here's the plots for 200%, the 3 samples, cycling it and performing. So we were able to repair the material without a problem. So those have been testing for just materials, but we also test assemblies. ASTM E2357 for air barrier tests, we're actually testing 2 different walls. We have a blank. You're testing air barrier membrane, whether it be sheet or fluid. And then you also have another 8-foot by 8-foot blank with a window, ductwork, pipe penetration, electrical boxes. So testing one versus another, you should be within 10% of each other. So this is an 8-foot by 8-foot test duct. We built our own test walls to do this testing for air. And similarly with your window penetration and electrical boxes and ductwork. Around the perimeter, you can see the silicone membrane, and in this case, we just had a window in the application. These were independently verified by an outside testing agency, but this was the specimen 1 with the blank, and then specimen 2 with the peel and stick. So if you went through the numbers, they were very easily within 10% of each other. But to make that connection easier, we came up with ETA, Poirier's ETA. It's a metal adapter attached to a window or wall frame. The adapter is extruded aluminum with an iodine finish, which is a pre-treatment for paint, but we use it for all structural glazing with silicone sealants. Holes are 6 inches on center. The butyl tape is pre-applied. This allows the contractor to position it on the window or wall frame, and then mechanical fasteners will hold it in place. Excuse me. Then you come back with a silicone sealant, apply a small bead along the edge, and then you take the gasket and make the installation. We designed the metal adapter to have an offset leg. This creates a small reservoir of sealant to bond the metal adapter to the window or wall frame, and then the excess sealant bonds the gasket into position. The silicone extrusions, which we've been doing since the early 80s, as you were looking at a Play-Doh extruder, The material doesn't have much structural strength until it's secured. So we were limited on the thickness. 1/16 of an inch was typically the minimum thickness you could extrude silicone without it tearing. But by going to these rib design, we have the structural strength for extrudability, but we were able to thin down the webs to a 32nd of an inch. Did two things for us. One, it gave us a mechanical lock into the sealant with these ribs. Then we thinned down the web to allow more elongation, less stress on the bond line for the sealant. And silicone sealants are not adhesives, they're sealants. They need some volume of material to perform as a product. So by having a 32nd of an inch of sealant on these ribs prevents the installer from squeezing it down to a film, so we have some sealant underneath the membrane to create that bond that we require. So just as an elevation detail, we would start at the bottom window and work our way up in pieces. So here we're showing the metal adapter. You peel off the release paper. This will be attached to the framing. Your sealant bead is applied. And from the exterior, we're going to do the corners first, so they're 5 inches in either direction. There are pre-molded corners with a dart. Just gets embedded into the sealant in the race and around the perimeter. Because the material is translucent, you're able to see through the gasket to ensure quality of contact area. You need 1 inch of contact area around the perimeter and just enough bonding on the side of the race. The gasket also comes in lengths of 100 feet. The darts are trimmed off so that you can create a 1 inch overlap. And then you do your step flashing up the vertical. Seal around the perimeter to make sure all those lap joints are done properly and along the edge of the adapter so that you have the contact at that condition. As you work your way up to the jamb, up to the head, you still do the next corner and then simple lap joints and then finish tooling it off. So here then they can put the pressure plates to set the glass, do your brick veneer or metal panels, whichever you're using. But now we make that connection from the window frame down, in essence creating a nailing flange or drainage plane for the window assembly. And the same at the head. This system was tested again at an independent test lab for 283, 330, 331, and 547. So these are the values we were able to get. Obviously 0.01 was the low number they'd give. 0 is not a number they like to give out. But we had no air or water leakage. These are the windows that were tested. We had 3 brought down, just the assemblies. Obviously, after testing for air, the water test was done. So we have a spray rack. So we subjected the surface of the air barrier and sealants to direct contact with the water. So here's some shots of negative 135, negative 150. Very little deformation in the material during this testing, but that was as close as we could get before they started loading it up. This window assembly we were able to take up to 195 PSF before we had to stop because the strap anchors were actually pulling out of the aluminum. The window itself was actually designed for 135 PSF, but having the strap anchors closer together, we were able to get the value up a little higher. The next window we were able to get up to 210 PSF before the strap anchors actually let go. So the actual attachment with the silicone sealant and the ETA gasket never had a failure. During this, Regents Hospital came about, and this was a unitized curtain wall, dry glazed, and they wanted to use our ETA assembly. However, the primary seal was along the perimeter of the metal, and we didn't have enough surface area to apply the adapter. So during the design phase, we moved the adapter inwards and extended the leg of the ETA from having an offset leg. It was actually moved back further than right in the glazing plane of the glazing pocket, mainly because it was a curtain wall and these screws are going to go through. We didn't want to go into the sleeve of the expansion joints. So 4 inches was the design position. So this is the extruded shape with an offset leg. We made 3-dimensional corners, so it would turn the corner of the curtain wall. So here's an illustration of the adapter was already pre-applied on a unitized wall system or window at this location. Here's just an exploded view of the gaskets around the perimeter, how they would be sealed in, and then your brick veneer, steel lintel, flashing, more air barrier membrane, sealant bead. But when you look inside, moisture going through either brick veneer or metal panels cannot have access to the window frame or curtain wall. So all the moisture has to collect and go around it. The wall manufacturer actually did thermal modeling and actually had an improved thermal efficiency because we're encapsulating the wall or window with the silicone membrane. This is a visual mock-up. Metal adapter being screwed in, but it's a very small bead of sealant that you embed the gasket. Here's just the sew condition. And then the cut lengths and molded corners were applied. So this is just during the sequencing, applying sealant for the lap joints. So here we've got a tooled lap joint and sealant beads on either side. And there's the finished product. So you've got at least a 1-inch perimeter sealant bead lap joints. During this initial installation, the corners were put on top of the gasket, but as you look at the bottom, the corner, well, you can't see it too easily, but wasn't properly shingle lapped. All our literature now does say to do proper shingle lapping or step flashing, so there was no edge pushing up the water draining down into it. But around the perimeter here, you can see the sealant bead. The slots for the weeps are left open since it is a dry glaze system, but they didn't have to put any metal end caps at the end of the mullions to seal it out. We've compartmentalized the window, so if the window manufacturer did not properly seal metal joinery, it cannot get back into the building. It will drain out through the glaze, out through the weep holes. Across the head of the curtain wall, it's all properly flashed and no water can get in from the outside. These were the window penetrations in the lobby area, and of course the look after the brick veneer is put in before the sealant beads are applied. Next system we have is system 3. Again, what we're looking at is getting away from the metal adapter and actually installing it right to the curtain wall. So looking at this, the bottom with your F anchor, the mill valve area, the mullion stem needed to be trimmed away. This will allow a sealant bead to be applied horizontally and then up the vertical. So we have one continuous contact area. So these are, again, corners that are 5 inches long, so you can glue it in place. It has a smaller dart. We designed these to fit everybody's metal, whether it would be an old Castle US aluminum, Vistawall, doesn't matter. The dart is designed to fit any of these race configurations. So it gets inserted. Obviously, you're letting out action again. And then the gasket is cut to length. Dart is trimmed off. Here's just a close-up of it, so you had to be trimmed off flush, just to create a 1-inch overlap. The small dart just gets plugged into that race, and the sealant squeezes out. And then you start to do your jams, and then your perimeter sealant bead. Then you work your way up to the head, and then across the head of the wall, curtain wall, and then tooling the sealant around the perimeter. Here you got your Dutchman, start setting your glass, pressure plates are applied, and then you could come in with your veneer, whether it be brick, and then come in with your sealant bead. Now the exterior sealant bead, snap covers, up close. Now this exterior sealant bead is just decorative. The interior seal is your primary seal back at the drainage plane of the curtain wall, again with the air barrier. Now in this case, obviously this wall is designed or drawn up to be everything in plane. Doesn't always come that way. A lot of the walls are being moved outwards to help create larger volumes of insulation. So in this case here, we've got a steel lintel where the curtain wall is cantilevered out from the wall. So we've manufactured 3-dimensional molded corners. So that could be stacked and create the stair step after trimming them around the corner. And then the other gasket just bends around the perimeter and then up to jam condition. If the wall is recessed into the rough opening, again, a sealant was applied, your molded corners trimmed down, embedded, and then your gasket around that perimeter. But now it's being recessed. Again, we only needed 1 inch of surface contact here around the perimeter, so the gasket doesn't have to move out to the outside face of the curtain wall or sheathing. Just needs to make sure there's sealant applied along that edge, so no moisture or debris can work its way underneath or inside the wall. We took this system and took it out to have it independently tested for these test methods. But we did a few more, since working out a lot more seismic conditions. So we were testing for air, static, water, and then dynamic loads, structural testing, but then we wanted to rack the unit for seismic conditions. And then we would repeat air and water, and then take it to destruction. This was the test methods, testing results we did achieve. Again, not giving a 0, but we were able to take this up to 150 PSF. We took a $1,600 planar pressure bar system, and we structurally glazed it in place because we didn't want to test the actual wall or window. We wanted all the stress to be put on the membrane connected around the perimeter. So the pressure plate was put on to mechanically hold the plastic in place, so we weren't going to let that go depending on what load we went to. So all the stress was going to be on the perimeter gasket. We made a small window because we were going to be racking it 2 inches in either direction. The bolts on the other side of the frame allowed us to mechanically move it, and we slotted the anchors to allow this to be moved. So here we have a 3-inch gap, so we could rack it 2 inches in either direction. So after getting that assembled, we wrapped the buck in the air barrier product. We dry fitted the molded corners. Again, you can see that the milling stem needs to be milled away. And during any testing, you always want to know where you believe your failure mode is going to occur. In this case, we only have between 3/16 and a 1/4 inch of surface contact area underneath this mullion, and no raceway to plug the dart in. So this is our weakest point of the whole system. So this is where we felt was going to be our failure mode or location. So here's just a shot of the dry fit of the corners, dry fit of the gasket cut length with simple 1-inch overlaps. So we started sealing the gasket in place and then finished off around the perimeter. Again, this showing how we had structurally adhered the plastic in place, so we didn't want to test the window at all. The testing organization built us a test chamber, put our buck into it. Just a view from the interior. Obviously, they're bagging the assembly to test the difference between the chamber and our assembly. Then testing for water, looking for any leaks. No leaks occurred, so they were able to do dynamic. 115 miles per hour was as high as they could do for Category 3 for sustaining 15 minutes. Some shots during the interior during that loading in water with no leaks. On the exterior, after no dynamic load, we went ahead and positively pressurized it at 100 psf. Here you can see the gasket being sucked in around the perimeter. And again, we left the pressure plates off from the corners because this is where we wanted to be able to do inspections while the testing was going on. So we were able to make sure that there was no bond or loss. We also didn't put any pocket fillers in. We wanted all the stress on the bond line of the membrane so that the pressure plates were not contributing to help hold the gasket in place. After passing the 100 psf loading, we went to racking the well 2 inches in either direction, 3 cycles. So here's the elongation on one side and the compression on the other. Our sealants and membranes, as currently used, would not be able to accommodate this. So these are just shots from the interior, showing and documenting that we did move it. We repeated the dynamic load at 115 mile an hour with water spray with no leaks. Then we subjected to 150 psf structural load. You can see it being sucked in around the perimeter. Now our negative 150 psf with no failure. Unfortunately, at this point in time during the test, the failure became the chamber itself. The plywood on the back side let go, and we couldn't take it up any higher than 150 psf. So you can see here we had very good adhesion around the perimeter. But the next day we took the buck inside to have it on our test wall. Since we no longer had a rack book system, we were just seeing what the net positive load could be, or highest load. So we were able to pass positive 175 psf without a problem. 175 negative, we started to have some deformation in the gasket, and it eventually tore. But we didn't have a tear in the membrane or adhesion. It was the actual gasket ended up failing on us. So this was, we couldn't report 175 as a finished number. 150 was the highest PSF loading. This brings us to New Parkland Hospital. During the design phase, we got into the mock-up and they found that there were going to be steel lintels in a lot of these openings supporting the window. Well, this would cause some issues of how to seal it properly. So with the cantilever F anchors and T anchors that we were going to have, we needed to be able to seal around these conditions. So working with the architect and the GC, we were able to get those stopped back short of the rough opening so they didn't extend past the window frame. This would allow us to bring in our molded corners to seal those. So that you would have a nice finished condition around the perimeter to make that continuous seal. Some of the windows actually sat out from the rough opening. So from the exterior, we were anchored on the outside. And as you can see here, they decided we were going to take the three-dimensional molded corner and make the transition from the air barrier. This was a liquid applied air barrier in Dallas, permeable. that can make that seal, and then take the rib silicone sheet in transition over the anchors. So at the bottom with your steel lintel, the screws were cut off. They could actually make the molded corner, seal it in place, and then just bond the silicone gasket to the bottom of the curtain wall and to the bottom of the steel lintel. Working their way up the jambs, going over the anchors, and across the head of the window. And that was your finished look. They had both stone and metal panels. The last project we have is Camp Pendleton. The ETA making the connection around the window wasn't in the condition they had, but they did have seismic drift joints. Looking at the actual sill condition, they had metal flashing wrapping around each of the openings that the sealant bead would make that seal. So at the head condition, again, metal flashing. And at the jambs, again, another piece of metal flashing, which had to work within a drift joint across the head of the curtain wall. So the architect worked a lot of different details and different components to do proper sequence of installation. So we drew this up in 3D. So here we have a rough opening, half of it, to the right, with a seismic drift joint across the head, which continued. So they would wrap the rough opening with a peel and stick product, and then starting at the bottom with the metal flashing, at the jamb, and then counter flashing with your air barrier membrane. Then we would allow you to put your sealant bead and silicone strip to create your seal for the drift joint. Then it would continue with the next piece of flashing, staggering it, shiplapping another peel and stick over the top of it. And this would allow now to take the three-dimensional molded corner to transition into that condition. And because the corners were only 4 inches in dimension, they had to come out over 6 inches. They just took a strip of the silicone sheet and bonded it. On the opposite side of the frame, some of these conditions, they'd have the membrane, the steel flashing, again, shiplapping the peel and stick, and then taking the three-dimensional corner, gluing it in place, and then making the extension. So these are some shots during the actual mock-up, during installation. So they've got the sill membrane and up the flashing and up the jambs. Here they've already got the metal flashing on top of the air bearer ETA gasket across the side of the drift joint. Here it is continuing it on to the right side of it. Molded corner. And then the outer side, step flashing it. So here are the job site conditions. Gluing in place. The opposite corner where they cut the corner down, not having to go out as far. And the finished look. And if you want to read more about the project, it's in the Military Engineer. And if you have any questions. And with that, any questions? Yes, slides of the presentation will be available for sharing, and I believe Kelly will put those on the link site. Emma or Kelly, or are you guys going to take control of this, or how do we handle it?
Do these same sealing techniques work on non-masonry buildings?
Yes, you could have it on a non-masonry building. It was just, we've sealed to metal panels. We've sealed behind, obviously, terracotta panel conditions. It just depends on what you're trying to get into. But it was just a connection, obviously, to an air barrier product. We've actually done projects where we weren't going to an air barrier. It was really just to a precast condition.
With respect to the UFGS specs, we are actually working on having them translated to the UFGS currently by our spec consultant, and we will forward those as soon as they are complete. Question. We'll be online for several more minutes. If anyone should have questions, feel free to audio or type them in. Thank you.